What if you could reach space without using a rocket? Imagine stepping into an elevator car at the equator. The doors close, the floor hums. Outside, the ocean falls away, then the clouds, then the blue edge of the atmosphere. Hours later, Earth is no longer beneath you. It is a glowing sphere turning silently in the dark. No launch tower, no violent acceleration, no controlled explosion. Just a climb. This is the promise of the space elevator, one of the most audacious ideas in engineering. In established physics, the concept is surprisingly simple. In practical engineering, it may be one of the hardest machines humanity has ever imagined. A space elevator is not a tower. No material could support a tower 36,000 kilometers tall under its own weight. Instead, it would be a tether stretching from Earth upward into space. At the bottom, it would be anchored near the equator. At the top, it would extend far beyond geostationary orbit, with a counterweight pulling outward. Elevator vehicles, called climbers, would grip the tether and crawl upward. To understand why it could work, we have to look at Earth's rotation. Earth spins once every sidereal day, about 23 hours and 56 minutes. At one special altitude above the equator, an object orbits Earth in exactly that same time. That altitude is geostationary orbit, about 35,786 kilometers above sea level. A satellite there appears to hover over the same point on Earth. That is established science. Communication satellites use it every day. A space elevator would use the same physics in a far more extreme way. If the tether extends past geostationary orbit, the outer section has an outward centrifugal tendency. Gravity pulls the lower section inward. Rotation pulls the upper section outward. Together, they can keep the cable under tension, like a rope being swung in a circle. But here the story turns from elegant to brutal. The cable must survive its own weight. It must hold climbers and tens of thousands of kilometers of itself. Steel is far too heavy. Kevlar is not enough. Even the best conventional materials fail by a huge margin. Engineers call the key property specific strength. Strength divided by density. Carbon nanotubes and graphene are often mentioned because, at tiny scales, they show extraordinary strength. That part is real laboratory science. The hypothetical part is turning microscopic wonders into a flawless cable longer than Earth is wide. It would need industrial production at a scale no one has achieved. A single weak point could be fatal. How would we build it? One proposed method begins in space. A spacecraft places a seed tether at geostationary orbit. One end is lowered toward Earth while the other extends outward with a counterweight, perhaps a large manufactured mass or captured asteroid material. When the lower end reaches the equator, ships or offshore platforms secure it to a movable anchor. The anchor would likely sit on the ocean near the equator, where it could move to avoid storms or debris trajectories. The tether would not hang motionless like a pencil line. It would vibrate, sway, and respond to winds, passing climbers, solar heating, the moon's gravity, and Earth's uneven gravitational field. Now picture a climber. It cannot carry rocket fuel for the entire ascent, or the advantage disappears. Instead, it might use electric motors powered by a laser or microwave beam from the ground, draw power from the tether, or use solar panels once high enough. The elevator does not make physics free. It changes the way we pay the bill. Rockets spend energy quickly, fighting gravity and pushing propellant at high speed. An elevator could spend energy slowly, using electricity. The ride might take days, not minutes. For cargo, that is acceptable. For humans, the cabin would need life support, shielding, and emergency systems during a long climb through every layer of the sky. The first kilometers are deceptively familiar. Clouds, wind, lightning, ice. Higher up, the atmosphere thins. The sky darkens. But danger does not disappear. The tether crosses regions filled with orbital debris and micrometeoroids. Even a tiny fragment at orbital velocity can strike like a bullet. The tether may need to be a ribbon instead of a round cable, with many redundant strands. If one section is cut, the load must redistribute before a tear runs catastrophically. Robotic repair climbers might constantly inspect and patch damage. Tracking systems would monitor satellites and debris. Spacecraft would need to maneuver around the elevator, creating a new traffic system in space. Safety would become a discipline of its own. What happens if a climber loses power? What if the tether begins to oscillate? What if a storm forms below? What if a segment fails? The answers are theoretical today. Braking systems, rescue climbers, detachable sections, emergency descent paths, and controlled release strategies. Every answer adds mass and cost. The cable would also pass through radiation belts. Electronics and passengers would need shielding. Thermal cycling would be severe. Sunlight, shadow, heat, cold, expansion, and contraction. Atomic oxygen, ultraviolet radiation, and charged particles can all attack the structure. For every breathtaking rendering of a space elevator, there is a spreadsheet full of hostile numbers. And now we reach the central obstacle, the one that decides whether this idea becomes transportation or remains a dream. The tether material. Not the elevator car, not the anchor, not even the energy beam. The cable. It must be strong enough, light enough, durable enough, manufacturable enough, repairable enough, and cheap enough. It must perform for years. It must resist defects, impacts, weather, radiation, and vibration across planetary scale. Today, we do not have such a material in usable cable form. That is established fact. But science does not stand still. Materials research is advancing in carbon nanostructures, high-performance fibers, self-healing composites, and ultralight lattices. The path from laboratory strength to industrial reliability is long. Aviation, computing, and rocketry all began with materials that once seemed inadequate. If a space elevator were built, what would change? The cost of reaching orbit could fall after the enormous initial investment. Satellites and space stations could be supplied more easily. Large telescopes, solar power platforms, and deep space vehicles could be assembled in orbit. Beyond geostationary orbit, payloads could be released with extra-orbital energy from Earth's rotation. With the right timing, cargo could be sent toward the Moon, Mars, or asteroids using far less rocket propellant. The elevator would become not just a route to orbit, but a slingshot at the edge of Earth. There are environmental and political questions too. It might reduce some launch emissions, noise, and local impacts. Yet construction would demand vast industrial resources, global cooperation, orbital regulation, and decades of maintenance. Who would control it? How would nations protect it? A structure this large would not be merely engineering. It would be economics, law, and trust. So, could we build an elevator to space? The honest answer is layered. The physics is real. Geostationary orbit is real. Tension structures are real. Electric climbing is possible in principle. But the full Earth-based space elevator depends on materials and manufacturing capabilities that do not yet exist. A smaller version may come first. On the Moon, gravity is weaker, and there is no atmosphere. A lunar elevator could use materials we already understand more easily than an Earth elevator. Mars might also be more forgiving than Earth. These worlds could become test beds for the technologies an Earth elevator would require. For now, rockets remain our working path to space. They are loud, expensive, dangerous, and magnificent. The space elevator remains quieter, a line in the imagination, stretching from the equator into the dark, held up by rotation and ambition. The question is whether civilization can master the materials, safety systems, orbital traffic, energy infrastructure, and cooperation needed to build a machine larger than any machine in history. Someday, a child might look up from an equatorial ocean platform and see a faint silver thread disappearing into the sky. A cabin of cargo might begin its slow ascent, not with fire, but with light. And the border between Earth and space might feel less like a wall and more like a road. Could humanity realistically build one someday, or will the space elevator remain one of the most beautiful machines we never made?